Another approach for MSE reduction is known as stratified sampling. Suppose we want to estimate theta, which is equal to the integral of gt dt over the region from A to B. We can divide the region from A to B into several intervals. Let's denote by x0 to x1, x1 to x2, etc., all the way to xk minus 1 to xk. Here, the x values are the bounds for these smaller intervals. So A is equal to x0, and xk, which is the upper bound of the last one of these intervals, is equal to B. Then we know that theta, which is the integral of g in the region from A to B, is equal to the sum of the integrals inside each of these smaller intervals. And this gives us a way to estimate theta using stratified sampling. Let's use xj. Let's use theta j to denote the integral from xj minus 1 to xj of gt dt. So that's the jth integral over here. Then a simple Monte Carlo estimator for theta j is theta j hat, which is equal to the sample mean of the g xij's times xj minus 1. So here, the xij's are random samples obtained from the uniform distribution between xj minus 1 and xj. So we draw a total of nj of them for the jth interval. Now, if we sum up all of the theta hat j's across all of these intervals that combined together is from A to B, then we know that theta hat s, which is the sum of all of these theta hat j's, is an unbiased estimator for our theta, because our theta hat j is an unbiased estimator for each of the theta j's. So the sum is also an unbiased estimator of our theta. So when the number of draws you obtain from each strata is equal, so in that case it's equal to n divided by k, then stratification achieves some level of balance in sampling over the interval from A to B. So thus, it reduces the variance of the Monte Carlo estimator. So in fact, we can show that the variance of theta hat s obtained this way will be less than the variance of the simple Monte Carlo estimator theta hat if we use the same total sample size of n. So for the simple Monte Carlo estimator, we obtain n draws from the entire interval, whereas for the stratified sampler, we obtain n divided by k draws from each of the k stratums. In other words, the variance of theta hat s is less than or equal to the variance of theta hat. I'm not going to provide the explicit proof here, but I'll just provide some ideas. So in order to show that the variance can be reduced through stratification, we can think about the strata as a conditioning variable. Let's denote it by I. So if we divide the interval A to B into 10 strata, then the conditioning variable I can take 10 possible values ranging between 0 and 10. And then we will be able to apply the law of total variance. By the law of total variance, we know that the variance of g of x is equal to the expectation of the variance of g of x conditioning on the stratum variable I, plus the variance of the expectation of g of x conditioning on I. Now, the second term here, variance of e of gx conditioning on I, is some kind of variance, so it has to be non-negative. Thus, we know that this thing is greater than or equal to the expectation of the variance of gx conditioning on I. So in our case, what exactly is the variance of gx conditioning on I? It's the conditional variance of g of x conditioning on that x is from a particular strata. So for example, the variance of g of x given I is equal to j is the same thing as the variance of g of xij, where xi is a draw from the j strata. So as an optional exercise, you can try to expand the variance of theta hat x, which is equal to this thing here. You can further substitute the theta hat j here by the sample mean formula that we use. And you'll be able to see how it relates to the variance of gx given I. Then by applying the inequality above, it should be able to give you that the variance of theta hat is greater than or equal to the variance of theta hat s. In other words, we can achieve reduced variance using the stratified sampler. Let's see an example of stratified sampler with our earlier integral that we tried to estimate. So again, theta is equal to the integral from 0 to 1 of this thing dx. I'm not going to read it again. So we will break the interval from 0 to 1 into 10 equally spaced strata and see how the variance of our theta hat will change with respect to the simple Monte Carlo sampler. That was our phi1. Again, we will use a total of n equals 10,000 samples for both the simple Monte Carlo sampler and the stratified sampling estimator. So to get the stratified sampling estimate, we first need to estimate theta hat j for each of the strata. And that is given by this formula here. Then we'll be able to take the sum of these theta hat j's, which gives us theta hat s, which is the estimate for our theta. So the steps that are outlined over here summarizes the procedures for this stratified sampling algorithm. First step is to divide the interval from A to B into stratas. In our case, we want to divide 0 and 1 into 10 equally spaced intervals, so each of them will have width of 0.1. Then for each of the strata, so for the J strata, we want to obtain a series of draws. So x1j all the way up to xnj of j, where nj is the number of draws we obtain from the J strata, from the uniform distribution between xj minus 1 and xj. And then after this, we will take their average of the gxij's and multiply it by the interval width, so xj minus 1, to get the theta hat for the J strata. The last step is just to sum them together. So by summing up the theta hat j's, we get our theta hat s. So for the integral we're trying to evaluate, 0, 1 is divided to 10 equally spaced strata, each with length 0.1. So xj minus 1 will be equal to 0.1 for each of those. And we will also use the same sample size for each of the strata. So with a total of 10,000 draws and 10 strata, we want to obtain 1,000 draws from each stratum. So here's the code that implements the stratified sampler. We first create a empty vector, so a 0 vector, where we will later store the theta hat j's for each of the strata into this 0 vector. Next, we decide what are the cutoffs for the strata. So what are the intervals? So in this case, we do a sequence from 0 to 1, And the length of the output is equal to 11. So there will be a total of 11 points, and that gives us 10 intervals. For each of these intervals, so the numbers you get from this will be 0, 0 0.1, 0 0.2, all the way to 1. So for each of these stratas, from 1 to 10, we want to first obtain uniform draws of size 1000 in the interval from xjsj to xjsj plus 1. And then we apply the gx function. And then we take the sample mean of the gx and multiply it by the difference between these two, which is 0.1. And that gives us theta hat j for the jth stratum. Lastly, we sum all of them up, and you can see that the resulting theta hat s we get is again close to 0.52. But what we're most interested in is actually evaluating the variance or the standard deviation, comparing it to the simple Monte Carlo estimator. So again, we will replicate each of them for 100 times. So we do simple Monte Carlo estimation for 100 times, and then we do the stratified sampling estimation for 100 times. Like before, we create a matrix that we use to store all of the theta hats. The matrix has 2 columns. Each column has 100 entries. So the first column will be used to store the simple Monte Carlo theta hat. And the second column will be used to store the stratified sampling theta hats. So you can see I told you the code will overflow if I put too many on the same page, but you'll be able to see the complete code in the Markdown document. For each of the replications from 1 to 100, we first do simple Monte Carlo. So 10,000 draws from uniform 0, 1, apply the G function, and then taking the mean gives us the theta hat of this replication for the simple Monte Carlo estimate. Correspondingly, we do stratified sampling. We repeat what we did earlier. So we did it earlier for just one replication. So we just want to feed it into the for loop. So we repeat it for 100 times. So here we create a theta hat j's vector. We sum up the vector, which is the line that is swollen over here. And that gives us what we should put into theta hat mat in column 2, which is the stratified theta hat. And let's compare the results. First, let's look at the means. We can see that the means for both the simple Monte Carlo estimator and the stratified Monte Carlo estimator are close to 0.52. And let's look at the standard deviations. This gives us the standard deviations for the simple and the stratified estimators across the 100 theta hats, rounded to 5 digits. And you can see that here, the standard deviation of the theta hats obtained using stratified sampling is about 10 times smaller than that of the simple Monte Carlo estimate theta hat, which means that we have achieved a significant increase in our efficiency. So we have talked about 2 methods for improving the efficiency of our Monte Carlo estimators. The first is importance sampling and the other is stratified sampling. Well, these 2 can actually be combined together. So the importance sampling technique can be combined with stratified sampling to further improve our efficiency of theta hat. Specifically, in order to estimate theta, which is equal to the sum of the theta j's in each of the strata, the theta hat j's we use to estimate theta j in each of the stratum does not have to be the simple Monte Carlo estimator. So earlier we used the simple Monte Carlo estimator and we drew random samples from the uniform distribution between the two bounds for that stratum. Well, it doesn't have to be this way. You can, if you want to further improve the efficiency, you can choose an importance function, phi of j, for each stratum. So you can choose phi of j wisely so that it is roughly proportional to g of x in each of the stratum. And then you can apply importance sampling to each of the stratum to get a good estimate of theta hat j. Summing them up will give you a theta hat s that is further improved in efficiency. And that concludes our chapter on Monte Carlo integration. So throughout the chapter, we learned about various methods for Monte Carlo estimation of definite integrals. So we learned about simple Monte Carlo techniques, importance sampling, and stratified sampling Monte Carlo estimators for definite integrals. We also learned about the properties of these estimators. So for example, whether they are biased. So all of them are unbiased and they are asymptotically consistent. And we learned about the efficiency of these different kinds of estimators. And we also know that we can apply the central limit theorem, and the theta hats will be asymptotically normal, and we'll be able to use them to get the confidence bounds. However, Monte Carlo techniques are not only useful for evaluating integrals, they can also be used for other kinds of statistical tasks. For example, for hypothesis testing. So next week, we are going to start a new chapter, and that will be Monte Carlo inference.